All right. Hey, welcome back to lesson 4. We're in unit 8 of AP Calculus, AB. And this unit, we're just continuing to grow in our understanding of the indefinite and definite integral and the fundamental theorem of calculus, which is why I call this lesson 4 the fundamental theorem of calculus again. You might recall that we really learned the fundamental theorem of calculus logically backwards. We learned the second part first. Well, now it's time for us to go back in time and learn the first part. So here we go. Well, before I say here we go, and then I'm about to say, actually, it's going to behoove us to do a little bit of reviewing so we kind of get our mojo going with the difference between derivatives and integration and how they work together. So I got a couple of sections of practice problems. I want to start by finding the derivative of each of these functions, and then we'll go over and check your work. So give it a try. Okay, so to find the derivative, you could call this dy dx, or y prime is short for dy dx, is 12x cubed. The derivative of 2 over x, this could be rewritten as 2 times x to the negative 1. So, in your mind, you're thinking, okay, this is 2x to the negative 1. So the derivative becomes negative 2x to the negative 2. But you might see people just get so used to it that they know, okay, that's going to be a negative 2 over x squared. And you can just go right to that point if you want. You don't have to, though. All right, on the next one, bring down the exponent. 12 times 3/4 is actually 9. And then this becomes, because 12 divided by 4 is 3, and 3 times 3 is 9. And this becomes a negative 1/4 when I subtract 1. Now, the derivative of e squared is 0 because e is a constant. E squared is still a constant. All right, let's try the next one. 3x to the 5th times sine of 2x. Hopefully you remember your product rule for derivatives. So derivative of the first is 15x to the 4th times the second, sine 2x. That's a 4. Plus the first times derivative of the second, and the derivative of sine is cosine 2x, and then times the chain of 2. Remember, when you take a derivative, it's derivative of a co that makes it negative. So I took the derivative of sine, which is not a co, so my answer is positive. All right, next one, we have to do the quotient rule. So g prime of x is equal to low d high. The derivative of secant is secant tangent minus high d low all over low low. And you can see how we could actually quickly remove a couple of x squareds, making this just x secant x tangent x minus secant x times 3 all over x to the 4th. Okay, next we have arc cosine. Hopefully you remember your arc cosine formulas. I'll call it dy dx this time since I used y prime earlier. So dy dx is u prime over the square root of 1 minus u squared. So 2x squared in parentheses, or you can call it 4x squared, but make sure if you write it like that, you put parentheses around it. And because it's of a co, it'll be negative. Okay, next practice set. I want you to practice doing some integrals. So I've got 1, 2, 3, 4, 5 different problems, some definite, some indefinite. Give it a try. All right, let's see how you did. Okay, I will go ahead and rewrite this one first. So 3x squared plus 5x to the negative 4 plus 2 sine x dx. All right, up the exponent by 1 makes this x cubed over 3 times 3 is just 1. Plus 5 up the exponent by 1, divide by the new one. And the integral of sine is cosine, but it's negative because the rule when you integrate is if instead of do you integrate a co, it's do you get co in your answer. If you do, you need to have it negative, plus c. All right, always have to add c when you do indefinite integration. All right, let's try the next one. All right, hopefully you did a u substitution here. We're going to let u equal x cubed plus 1, this inside portion here, so that du is equal to 3x squared dx. And since I have x squared dx, which almost looks like this, I can just solve for that by dividing by 3, and I get 1/3 du equals x squared dx. All right, let's rewrite our integral. The bounds need to change to be in terms of u. So plug 1 in for x, you get 1 cubed plus 1 is 2. 2 cubed is 8 plus 1 is 9. And this x cubed plus 1 is u, so u squared. And dx times x squared became 1/3 du. I'll pull the 1/3 out and call it du. So now we'll integrate. U squared becomes u cubed over 3. And we'll be doing that from 2 to 9. So this ends up being, I can just factor out of 3, 1/9, 3 times 3 on the bottom. And I've still got u cubed to handle from 2 to 9. I don't know what 9 cubed is, and I don't really feel like finding out right now. I know 2 cubed is 8, though. So, anyway, maybe I could distribute the 1/9, and then I'd only have 9 squared, so it would be 81 minus 8 over 9, something like that. But I'll just leave it like that. Okay, let's try to look at the next one. Okay, hopefully you did another u substitution here. We'll let u equal 2x cubed. So du equals 6x squared dx. And since I have x squared dx, I'll just make this 1/6 du equals x squared dx. So this becomes the integral of simply cosine u, and x squared dx became a 1/6 du. The integral of cosine is sine u plus c. So this is 1/6 the sine of 2x cubed plus c. All right, let's take a look at the next one. Ooh, how do we handle this? Do you recall that if the degree of the numerator is the same as the degree of the denominator, you should try long division? So let's do that. Let's try x squared minus 2x. And that's what that fraction bar means. It means divided by. So let's just do what it says. It says it's dividing. Let's do dividing. Okay, x squared goes into x squared one time. 1 times x squared is x squared. 1 times 2x is a plus 2x. But remember, when you do long division, first you divide and we look only at the first term, x squared and x squared. Then we multiply everything by that, and we have to change the sign. Oh, and you know what? I did not finish. 1 times x squared, 1 times 2x, and 1 times 4. So I need to do a plus 4 here, and then to subtract them. After we multiply with the subtract, so I'm going to go through and change all of these signs. And what do I get left? That cancels out, but this gives me a negative 4x minus 4. So what that means is, since x squared minus 2x over x squared plus 2x was 4 has a quotient of 1, 1 plus the remainder, which is negative 4x minus 4, over the divisor. I always just put plus and the remainder over divisor. If you want to get cute and try and pull out that negative, you'd have to factor it out of both of these. So be really careful if you're going to do something like that. Okay. Now that we've done that, how close is this to being able to be done by u substitution? Well, I'm actually going to split this up a little bit because I don't need a u substitution to do that one. That's easy. So I'm just going to call that x and be done with it. So it's x plus whatever this ends up being. Well, I'll let u be x squared plus 2x plus 4. Then du becomes 2x plus 2. You'll notice that's really close to this. I'm sorry, dx. That's really close to what we have at the top. I'm just going to multiply both sides by a negative 2. So negative 2 du would give me a negative 4x minus 4 dx. So I can replace this with negative 2 du. So I'll bring out the negative 2, and I'll just call that du over u. And we know what that is. That is the natural log of the absolute value of u. And if you don't mind, I'm going to go ahead and put in x squared plus 2x plus 4 as we go. And technically, x squared plus 4x plus 4 can never equal 0, and it can never be negative is the important part. You could try and use the quadratic formula on that. You'll find out that it never equals 0. So I'm going to just go ahead and call these parentheses instead of absolute value because I don't need them. All right, so x minus 2 natural log of that stuff plus c. All right, let's do letter E, another definite integral. I'm going to let u be arc cosine of x for a couple different reasons. One of those is that we don't have a formula for the integration of arc cosine, so but we better let it be that one. The derivative of arc cosine is negative u prime over the square root of 1 minus u squared. Well, that's pretty close to what we have, except for we don't have this negative here. I have to divide it over. So I'm going to rewrite this with the negative on the outside. The dx, this dx is on top, by the way. I could have written it up here or just to the side. It would still multiply the top. So dx over 1 minus the square root 1, dx over the square root of 1 minus x squared is negative du. So that takes care of my du. And arc cosine was u, so we'll just put a u there. Now I got to change my bounds. What is the arc cosine of 0 if I plug 0 in for x? That's asking what. Remember the range of arc cosine is the first two quadrants. What in the first two quadrants does the angle have to be for the cosine to be 0? Well, that angle would be pi over 2. And then the next one, we have to ask ourselves, what, when we do arc cosine of root 2 over 2, what angle do you need to have for the cosine to be root 2 over 2? Well, that would be pi over 4. All right, now we'll integrate. And I just get u squared over 2 from pi over 2 to pi over 4. Plugging in gives me, I'll pull out the 1/2. Pi over 4 squared, so that's pi squared over 16, minus pi over 2 squared, that's pi squared over 4. We could get some common denominators there, make that 4 pi, make negative 3 pi squared over 16, and then positive over 32. But I'm just going to leave it like that. All right. So the first part of the fundamental theorem of calculus involves the relationship between integrals and derivatives. Now that we've practiced integrals, we practice derivatives, we're ready to put them together. So we have to do both to do this problem. We have the derivative with respect to x of the integral from 1 to x of t squared dt. So that's a little weird. We have x in our bounds of integration, but let's just go with it. So we need to start inside out. This is on the outside. We've got to start on the very inside, the integral. So integrating t squared, I get t cubed over 3. And my bounds are from 1 to x. And then I'll be taking the derivative with respect to x of that. So what does that become? Well, that becomes the derivative with respect to x of, plug in the top minus the bottom. So that becomes x cubed over 3 minus 1 cubed over 3. Now we have to take the derivative of this. When I take the derivative, the 3 comes down, and I get 3x squared over 3. Well, that's just x squared. And then this 1/3 cubed is just a constant. So this is the answer, x cubed. So what we're saying here is that when you have some equation and you integrate it, that somehow when you take the derivative of it, it ends up going back to something like how it started. It's almost as if derivatives and integrals are inverses of each other. And that's really what this is saying, that they can undo each other. That we can, if we integrate and then derive, we kind of cancel that process out. Let's take a look at another one. Okay, the derivative with respect to x of pi over 6 to x cosine t dt. Okay, so first we're going to integrate. The integral of cosine is sine. And we'll be doing that from pi over 6 to x. I'll then replace sine of t with making it sine of x minus sine of pi over 6, which is 1/2, but that doesn't matter because now I'm going to take the derivative with respect to x, and that's just a constant. The derivative of sine is just cosine. And so there we have it. So the fundamental theorem of calculus, part 1, says that the derivative of an integral from a to x of f of t dt is f of x, simply a change of variables. So we typically use something like t You don't want to use x as the function and integral bounds, so that's why we use t there. Notice that the a is the constant, the number. It has to be on the bottom and the x on the top. Okay? All right, let's try this one. Let's evaluate the derivative with respect to x from x to 4 of t squared. There's a couple different ways I could say what this becomes. Let's go back, instead of using the theorem we just discussed, let's go back and integrate again. So we could say this is the derivative with respect to x of t cubed over 3. And we're going to go from x to 4 this time. What happens there? The derivative with respect to x, and I get 4 cubed over 3 minus x cubed over 3. Well, the derivative of this is just 0, and then this becomes negative. Bring down the exponent, 3x squared over 3. This becomes just negative x squared. So having these bounds where the x is on the bottom and constant on the top changed the sign. It almost stayed, just became x squared, but it changed the sign. And the reason why I would say the simple explanation besides this work is that we know that this is equal to negative the integral from 4 to x of t squared dt. So we know that you can flip the bounds in an integral as long as you make it negative on the outside, because that's a true statement that flipping the bounds negates the integral. Now, then I know that I can bring the negative outside of the derivative. So this is just negative the derivative of that, and I have a theorem that tells me that is just x squared. All right, so in general, we'll say that the derivative with respect to x, some value x up to a of f of t dt is negative f of x. All right, the Fundamental Theorem of Calculus Part 1 chain rule version, let's take a look at that. So when this integral up here is actually a function, what we have to do is replace it inside f like this, and then multiply by the chain. Okay, so we plug in g exactly as it is, but multiply by the chain. In fact, we could have been said we were doing that earlier, but we were dealing with just x, which has a derivative of 1. So be on the lookout for that. Okay, so on here we have the derivative with respect to x of the integral from 3 to x of 1 plus t squared. That is super easy to do because I know the derivative of an integral from a constant to x just cancels each other out. Don't change a thing, but make t into an x and you lose your dt. All right, next, the derivative with respect to x from 2 to x of tangent of t cubed dt. Easy cheesy. Just replace it like that. Okay, now we get to exercise our knowledge of the chain rule version, so we'll do that. We're going to say 1 over 1 plus x cubed, because I just put that right there. But now I need to multiply by the chain of what? Of this. Be careful. Don't multiply by the chain of your expression of this part at the top of your integral symbol. That's your chain. 3x squared. All right, we'll do the next one. We have the cube root of 1 plus what goes where t is, sine. So I can call it sine squared x. Now I need to multiply that by the derivative of sine, which is cosine x. Okay, lastly, I have an accumulation function example. The accumulation function, you might remember, we talked about that earlier, but we didn't use the letter x. We said, look, the Fundamental Theorem of Calculus says that the integral from a to b of f of x dx, or excuse me, f prime of x dx is equal to f of b minus f of a. And we notate it by taking the integral, and we use this little box around it and all that. But if I move this f of a over, then what we get is an interesting kind of story. So whatever value your function's at a, adding up all the amount that it changes over time from a to b gives you the amount at b. And this is thought of very simply when you think about f prime being, the amount of, say, rainfall per day. And so the amount of rain that's fallen today plus the amount of rain each day for the next 5 days will tell me what it'll be, the total in 5 days. So in general, we're going to say the accumulation function is f of x equal to f of a, the starting value, plus the integral from a to x of f prime, the derivative of t, f prime of t. So if you're given the accumulation function that f of x is equal to f of a plus the integral from a to x of f prime of t dt, what's the derivative of f prime of x? Well, let's find out. F prime of x would be equal to the derivative of fa. Well, that's just a constant, right? So it's just the derivative with respect to x of the integral from a to x of f prime of t dt. Well, we know that this is just f prime of x. So the accumulation function, the derivative of the accumulation function is simply f prime. It's simply this equation here. And that is all we have for this lesson. So I will see you in the next one where we're going to practice that accumulation function lots more.